Hi everyone, I am Dr. V. Vasudevan, Associate Professor of Physics at K.S.Rangasamy College of Technology. Today I will be discussing Module 1, which is Semiconducting Materials from the course Physics for Computer Technology. Semiconductors are the foundation of modern electronics. Without them, we would not have computers, smartphones, or even the internet. So let's begin the session. In this session, I will cover five main points. First, we will look at introduction and the history of semiconductors. Next, we will discuss why semiconductors are so important. Then we will see the classification of solids and the basic properties of semiconductors. After that, I will explain the types of semiconductors, intrinsic and extrinsic, and how conduction occurs in them. Finally, we will touch upon carrier concentration, which is key concept for device design. Now let us see uh, the introduction part. The story of semiconductors began in the late 1940s. In 1947 at Bell Labs, John Budin and Walter Brattain built the first working point contact transistor using germanium. This invention changed the world. In 1948, William Shockley developed the junction transistor, which was more practical and paved the way for large-scale use in electronics. Initially, germanium was used as a semiconductor material. However, around 1950, researchers succeeded in purifying silicon, and by 1960, silicon devices dominated the electronic field. Why silicon? Because it is abundant in nature and inexpensive and can withstand higher temperatures up to 200 degrees Celsius when compared to the germanium, which fails above 85 degree Celsius. Thus, silicon became a backbone of modern electronic devices. Now let us see why semiconductors are so important. They are foundation of modern electronics. First, semiconductors enable miniaturization, that is, making devices smaller, lighter, and more powerful. Second, they allow high-speed processing and energy efficiency, which are essential for computing. They are also crucial for data storage and cost-effective mass production. Most importantly, semiconductors drive innovation and future technologies. Emerging areas like artificial intelligence accelerators, neuromorphic computing, and even quantum computers depend upon semiconductor technology. So, semiconductors are not just materials, they are enablers of progress. Now, let us see the classification of solids. All solids can be classified into three categories based on their electrical properties. First one, conductors such as copper and aluminum have free electrons and very high conductivity. Second one is insulators like glass and rubber have no free carriers and very large energy gaps as in the figure. Semiconductors such as silicon and germanium falls in between. They have a smaller energy gap which is shown in this diagram, which means that conductivity can be controlled. This ability to tune conductivity makes semiconductors unique and extremely useful. Now let us see some basic properties of semiconducting materials. Let's look at some key properties of semiconductors. They are formed by covalent bonds in a crystalline structure at absolute zero temperature. The conduction band is empty and the valence band is almost full. The energy gap is small for semiconducting materials, about 1.1 electron volt for silicon and 0.72 electron volt for germanium. Uh, they show a negative temperature coefficient of resistance, which means resistance decreases as temperature increases. Most importantly, their conductivity can be enhanced by adding impurities, a process called doping. These properties from the basics of electronic devices. Now let us see the classification of semiconducting materials. They are classified into two types. One is intrinsic semiconductor and extrinsic semiconductor. Intrinsic semiconductors are called the pure semiconductors. Extrinsic semiconductors are called the impure semiconductors. Extrinsic semiconductors are further classified into two types, that is N-type and P-type. N-type semiconductor material is formed by doping of pentavalent impurity, and then P-type semiconducting materials are formed by the doping of trivalent impurity. Now let us see how the conduction in intrinsic semiconductor. Now let us consider intrinsic semiconductors. These are Pure semiconductors without impurities. In intrinsic semiconductors, conduction occurs when covalent bonds are broken by thermal energy. When bond breaks, an electron becomes free, leaving behind a hole. Both the electron and the hole act as charge carriers. The energy required to break bond is the band gap, which is about 1.1 electron volt for silicon and 0.72 electron volt for germanium. However, conduction in intrinsic semiconductors is relatively weak and strongly depend on temperature. That is why in real devices we rely on extrinsic semiconductors. Now let us see how the conduction occurs in extrinsic semiconductors. Extrinsic semiconductors are formed when we add controlled impurities to a pure semiconductor. This is called doping. If we add pentavalent impurities like phosphorus, arsenic, or antimony, we get N-type semiconductors. These impurities donate extra electrons. So electrons are the majority charge carriers. If we add trivalent impurities like boron, aluminum, or gallium, we get a P-type semiconductor. These create holes as majority charge carriers. Through doping, the conductivity of semiconductor can be increased by millions of times. So this is the basic principle behind all diodes, transistors, and integrated circuits. Now let us see the difference between elemental and compound semiconductors. Actually, elemental semiconductors are called the intrinsic semiconductors, and then compound semiconductors are called the extrinsic semiconductor. Now let us see the difference. Uh, Elemental semiconductors are made up of single element like silicon or germanium. They usually have indirect band gap. So when electrons and holes recombine, energy is released as heat. These are mainly used in electronic devices like diode and transistors. In the case of common semiconductors such as gallium arsenide, gallium phosphide, and cadmium sulfide, which are made up of two or more elements, they often have direct band gap. So which means the recombination of electrons and holes release photons or light. This makes them ideal for LEDs, laser diodes, and optoelectronic devices. Thus, elemental semiconductors dominate electronics, while common semiconductors dominate optoelectronics. Now, let us see the carrier concentration in intrinsic semiconductor. Let us consider carrier concentration, the number of free electrons and holes in semiconductors. In intrinsic semiconductors, the carrier concentration depends strongly on temperature and the band gap. As the temperature increases, more covalent bonds break, producing more electron hole pairs. In extrinsic semiconductors, carrier concentration depends mainly on the dopant atoms. For example, in N-type material, the concentration of electron is determined by the donor impurities. So, understanding carrier concentration is fundamental because it allows engineers to design and control semiconductor devices for specific applications. Here we can see the density of electron in conduction band. So this can be calculated by using the density of states. So here we can see that is density of electron Ne is equal to 2 into 2 pi Me star kpt by h square whole power 3 by 2 into e power ef minus ec by kpt. Similarly, density of holes in valence band, that is NH is equal to 2 into 2 pi mh star kpt by h square whole power 3 by 2 into e power ev minus ef divided by kpt. So here Me and MH is the mass of electrons and holes. And then Kpt is the Boltzmann constant, H is the Planck's constant, Ev is the valence band energy level, and Ec is the conduction band energy level. Ef is the Fermi energy level. So this is about the carrier concentration in intrinsic semiconductor. In coming videos, I will explain how to calculate the carrier concentration in extrinsic semiconductor. Finally, I will summarize this session. Semiconductors occupy a special place between conductors and insulators. Their conductivity can be controlled by temperature and doping. Intrinsic semiconductors conduct weakly, but extrinsic semiconductors created by doping are the basics of modern electronics. Elemental semiconductors like silicon dominate electronics, while compound semiconductors like gallium arsenide are used in optoelectronics. Finally, carrier concentration is a key parameter in device design. So, semiconductors are not just a material; they are the foundation of all modern computing and future technologies. So, with this, I conclude this session. Thank you for watching this video. Thank you.